Welcome to the second lecture for Materials for Additive Manufacturing, Module 1. We are still looking at thermoplastics. Now we'll build off from what we learned in the overview and look into properties of thermoplastic materials and how they can be modified. The modifications are necessary for being able to 3D print them into different shapes. Here is an example of a couple of different complex structures printed by ASS Machine Bow. In reviewing polymer properties, we indicated that they are used typically either as powders or filaments in 3D printing. In addition, they can be used in a sheet form as well. For thermoplastics, you have a reversible phase change between solid and fluid depending upon the heat that's added or removed. The softening from a solid to a fluid occurs in a range rather than a specific narrow melting point. There are weak bonds between the molecules that more or less define properties, including the mechanical properties, their resistance to solvents, and so on. Covered in the last lecture that polymers were materials with large molecular weights and with a wide molecular weight distribution, and it's because of this distribution that you have the melting point occurring over a range of temperatures. Also, increasing the molecular weight increases the melting strength but also reduces the fluidity, so it increases the viscosity and so affects the processability. We looked at this generalized property chart as a function of molecular weight, and so melting temperature goes up, tensile strength goes up, viscosity goes up as you increase molecular weights. This could be plotted not only as a function of molecular weight but also as a function of temperature. Here in the idealized plot, you have deformation resistant, and depending upon the chemical structure and the molecular architecture of the chain, you could have a range of transition behaviors going from a purely glassy region for an amorphous polymer to a complete melting point without any glass transition for a perfectly crystalline polymer, which is basically the ideal case. But in most cases, for semi-crystalline polymer, you will see a combination of a glass transition and a melting point with a rubbery phase that is thrown in between at temperatures between Tg and Tm. We look at the inclusion of additives and fillers for modifying properties of polymers. Here are a broad range of colors that can be incorporated to change the appearance of the product. And when 3D printing was largely for form rather than functionality, this was an important way for communicating the appearance. As functionality began to get an important feature, for instance, you could add conductive fillers and improve the conductivity of printed regions to create circuits. So you would be able to have, in addition to a mechanical structure, an electrical component added in. We saw that there were a range of properties in terms of improving stability, improving mechanical properties, improving surface properties that could all be modified. In the aspect of conductivity, in addition to electrical conductivity, you can also change other aspects, such as in the medical context, which is an important application for thermoplastic 3D printing. You can improve the response of the polymer to the biological environment. So you could improve or increase the growth of cells around the polymer. You could increase the degradation of the polymer as the cells around the implant grow. And an important attribute, you can add fillers to improve bone regeneration, so hard tissue in addition to soft tissue. And bone regeneration and properties of fillers that improve that response is called osteoconductivity. We'll see more of that during some of the examples of research studies for developing new polymeric materials as we advance through Module 1.